Okay, so let's look at this set of the paper, which is May June 21, okay, paper 2122. Okay. So for the first question here is about the system of equations question. So we want to show that okay, this system of linear equation has a unique solution. So what we have for the situation here is, okay, we have to first take out the matrix for this system of linear equation here, and we are trying to find the determinant of it. So it's all the time, okay, about the determinant. So we want to prove that it has got a unique solution, okay, with the condition that the a is an integer here. So we could find out what is the expression for the determinant here, okay. So it's either we can argue that the a, okay, if it is an integer here, then our 26 minus 11a, which is this expression for the determinant here, would not be 0. Okay, so in the case here, so the equations will actually have a unique solution. Okay, or you can actually try to solve when we have got the 26 minus 11a is equals to 0. So you can actually solve for the a, you're getting like a 26 over 11. You can mention here this is not a integer. Okay, so you can also do something like that. So in this case, we will have with these two types of the proof here, then you can mention that okay, it is actually a unique solution. So another situation that we need to interpret this situation geometrically. So that is we have to mention about like, okay, this is the case that the three planes intersect at a single point, or you can say intersect at one point like that. Okay, you have to mention about that. Okay, what is going next, okay, for the next part here is, okay, find the value of a for which x equals to 1, y equals to 4, z is equals to -2 is the solution to the system of linear equation in part A. So you can notice that this is actually just a 1-mark question. So it should be very easy to be done, right? So what we have, okay, is the idea is that, so because this x, y, z here is something that is that is able to satisfy the equation, because it's a solution of the system of linear equation set. So these three values of the x, y, and z should be able to satisfy the equation. So it allows us to actually sub into the equation that contains the a, that because it should satisfy the equation, right? So from there, we can actually find the value of the a very easily here. Okay. So that would be what we have for the part B here. Okay. So for the next question, it's a differential equation question. So we need to find the general solution for y in terms of the x here. So what we have, okay, for this case would be like left-hand side, okay, to get the auxiliary equation. So everything is as usual. So getting the auxiliary equation, solve the roots from the auxiliary equation, and that is where we have got the particular solution for the y there. Okay, that would be the particular solution. And after that, what we need to do is, okay, now we got to find out sorry, this is a complementary solution. Okay, this is a particular. So the particular solution is depending on the right-hand side. So in the right-hand side, we've got the linear function. So the particular function that we have here is also like a linear. So we make it to be like ax plus b. Okay, so we differentiate. So we get a, and also we get a 0 from there. So which we could actually sub all these, okay, into the equation. So we could now tidy up and solve for the equation there. So we can compare the x with the x. So we get the a. So with the value of the a, we are able to solve for the value of the b here as well. So that will give us the particular solution, the yp there. So finally, we will actually have the general solution. So because here they didn't give us a value, so we do need to sub in and find the value of it. Okay, so this would be the general solution for this equation here. Right? So in the second part here is to state an approximate solution for the large positive values of the x. So this is when we are looking at the x approaches infinity. because that is a large and also a positive value. So when the x approaches infinity, so all the e power negative terms will actually approaches 0. Okay, so at the end, what is actually left is just like the x minus 1 for our y here. Okay, so that is just 1 mark. Okay, so that is just a 1 mark question. So, and the question is a 6. So we don't really have to show the working here. We just need to understand ourselves, like how to actually get to the final answer here. Okay, they just want to look at the final answer here. Okay, let's look at the next question. So this is the question about rectangles. Okay, so we have got this is the curve of x cubed, and then the x is from 0 to 1. So together with the set of the n rectangles with the width, which is 1 over m. So by considering the sum of the areas of this rectangle, show that the integral of the x cubed is less than the un. So the un is given by this expression. So the un here is the upper bound. Okay, so this is the upper bound for the area under the curve. And usually, okay, the figure given is for us to solve for the first part. Okay, so very easy here. We just need to find out what are the heights and what are the areas. Okay, the areas of these rectangles are given by the width 1 over n multiplied by all the heights there. So the height of this rectangle, okay, you can see that the height here starts with the x is equals to 1 over n. Okay, so the height is we substitute into the x cubed there. So this is the height of the first rectangle, followed by the second height of the rectangle is given by x is equals to 2 over n. So we sub the 2 over n inside there, inside the function to get the height there. And lastly, it would be the 1. Okay, so 1 cube would be the height of the rectangle. So in this case, when we try to calculate the un here, that is where we try to factorize the 1 over n cube out. Okay, we try to factorize the 1 over n cube out to multiply with the 1 over n. So we get 1 over n power 4. And then inside there, what remains are all these like 1 cube, 2 cube, and so on until the n cube. Okay, basically here we just need to apply. So this is the sum of the cubes. Okay, from r equals to 1 to the n here. Okay, so after that, we just have to do some cancelling, tidy up, then we should be able to obtain the expression which looks like this. Okay, so this is our upper bound. Okay, so the similar idea would be applied to find the lower bound. Okay, so the lower bound here is we got to make the rectangles shorter. So it means that the first rectangle will have the height which is a 0. The second rectangle will have the height when the x is 1 over n in this case here. And the last rectangle will have the height of the n minus 1 over n. Okay, so we do the similar thing. So we use the width to multiply by all the height. So the first height starts with the x equals to 0. The next height is when x is equals to 1 over n. And the last height that we have here is the x is equals to n minus 1 over n here. So in which we factorize the 1 over n cube out. So to multiply with the 1 over n before, so we get 1 over n power 4. This, okay, the thing that we have here is the sum of the r cubed from r equals to 1 to the n minus 1. So sub in the formula accordingly. Okay, and we can tidy up and so on. So finally, this would be the expression for the lower bound that we have for this ln. Okay, here. Okay, so the rectangles question are mostly like that. Okay, so next. So this is to find the solution of this differential equation. Okay, and what happens is that they already give us the hint, or this is the thing. So integrate a cosecant of the d theta is a ln of a tangent half theta there. So we can use this straight away. So okay, what happens is that first, this equation is not in the standard form, right? So if it is not in the standard form, then we have to divide. Okay, then we have to divide by the sine theta. Okay, so once we divide by the sine theta already, so we will take the coefficient of the y to integrate. So put it as the e power, the coefficient of the y, we integrate it. So basically 1 over sine is a cosecant. So we can use a hint there. So integrating a cosecant gives us a ln tangent half theta. So of course the e power law will get like cancel off. We are only dealing with like the tangent half theta there. Okay. So okay, let's look at the thing here. So for the tangent half theta here, we need to multiply that to the equation. Okay, so the equation that we are referring to is this form. Okay, the standard form, we got to multiply by tangent half theta for the whole thing there. So, okay, we will have something like this. For the left-hand side, it looks very complicated, but it's okay. Because later on, we will always get like the d of d theta of the y multiplied by the integrating factor. It's always like that, no matter how complicated the left-hand side is. So the part which is a little bit more headache would be the right-hand side. So in the right-hand side, we could observe that is we have got like a tangent square, okay, and then the angle here is a half theta. And then also we have got something which is like the cosec theta there. They have different angles. So our strategy would be, because since like we see we have got a lot of the half thetas there, right? We just change, okay, the cosecant theta to the something related to the half theta there. So of course, cosecant theta here is 1 over sine theta. So we use the double angle formula, okay, to give us like 1 over 2 sine half theta cos half theta, in which we could sort of cancel off some of the things there a little bit. So we can cancel off the sine, and this is what we get. Okay, so this is sine half theta over 2 cos cube half theta. There are different ways that we could deal with that. Okay, my way of dealing with it would be, okay, so my way of dealing with that would be I'm actually using the fact that, okay, we can simplify that until we get like the secant squared and tangent term. So how do we actually integrate it later on? Okay, when we bring the d theta over, we will integrate it, right? So how do we integrate it later on is that because differentiating a tangent will give us a secant square. Okay, differentiating a power of the tangent will give us a secant square, or differentiating a tangent will give us a secant square. So we can think of, okay, when so what have we differentiated such that we get this thing here? Okay, so we have differentiated a tangent square. Then only we will get a tangent with a power 1, and then we have got an extra secant square term there. Because differentiate tangent gives us a secant square. Okay, so you just look at, okay, how do we differentiate this? We bring down the 2, and then we need to differentiate the tangent half theta itself. So then we have got like secant square half theta, and then multiply by another half there because of the half theta there. So this gives us this whole thing straight away. Okay, so this is my way of trying to do that. So another way would be you could try to use the fact that you can let the u to be cos half theta. Okay, you can use the u is equals to cos half theta here. Then you are actually able to get something which is in terms of the secant square. Okay, you get something which is in terms of the secant square. So when you get the secant square, it's not wrong as well, because although I have got the tangent square half theta there, right? If you get the thing which is in terms of the secant square, then it will be something that is like half secant square half theta plus some constant. Okay, why? Because tangent and the secant square here, they are related by an identity. So still the answer is like, this is actually like correct one. Okay, so if you use the this substitution, you will get something that is secant square. It's also correct because the difference is just like one is in tangent square, one is in secant square, because they could be related by some identity. So it's not wrong. Okay, so no matter which form that we get from there, then we still have to substitute the constant into to look at the values of the constant. So the value of the constant that we will have here, if we are using the tangent square, that one, it's a half theta. So you can see here, it's the fact that, okay, for this, when we sum in the c equals to half theta inside there, right? From here, right, the right hand side, you can also look at it as like a half, which is 1 plus tangent square half theta, which is giving us secant square half theta. Okay, so different form. So if I'm remaining into like this form, right, I just have to bring the tangent over to divide by 1 of it. So this is one form that we could get for the y there. Okay, in some other way, you might actually have got like different expressions that which will actually lead us to the same expression at the end there. Okay, so for this question, it is not just having one solution, but you might have something which is in other form, but they should be equivalent. Okay, so this is why this question is so special here. Okay, so let's look at the next one. Okay, so number 5. So state the sum of the series. So basically, this is like a GP. Okay, this is a GP. So you just have to apply the formula of the sum of the GP. Okay, first term is Z, ratio is Z, number of terms is N. That's it. Okay, you get this formula here. So, okay, if Z is an n root of the unity and Z is not equals to 1, so deduce that we have got this result here. Basically, okay, this is some common technique that we use. Okay, it is not like coming out from nowhere one. So this is a common technique that we use all the time. Because we know that okay, Z is an n root of a unity, which is like Z power n is equals to 1. So we can actually express that as like a Z power n minus 1. Okay, and for this, right, we know that Z equals to 1 is a root. So if Z equals to 1 is a root, Z minus 1 is a factor that we can factorize it out, and then inside there it will give us a polynomial which is in which is having the highest power is at n minus 1 there, and this is always a form 1 plus Z until the Z power n minus 1 there. Okay, so after that, okay, what we will have, okay, is because they just asked us to deduce this is equals to 0. So we need to mention about, okay, now if the Z is not equals to 1, so we are not looking at this factor here. So the rest of it, okay, would be equals to 0. Okay, this is a very common technique. So it doesn't just come out from nowhere, right? Okay, you have to be aware we have got this thing, like this kind of the technique to work with. Okay. So now, okay, given instead that the Z is 1 over 3 cos theta plus I sine theta, so use the Morse theorem to show that we have got this thing. Okay, so there are two things that we want to do. One is we want to see where can we find this, okay, the left-hand side there. So we could obtain it by considering that, okay, because you can see this is sum to infinity, right? So for this sum to infinity here, okay, we are considering, because it already gives us a Z is this kind of the thing here. So let's just apply the Z. Okay, so let's try to sum the Z power m there. Okay, so we're trying to form this. So when we try to sum the Z power m there, right? Okay, so it's this is a Z power m. So from there, the 1 over 3 power m becomes like 3 power negative m. And this cos theta plus I sine theta power n, we use the Morse theorem. And from there, we can expand already. Okay, so from here, we already obtained the left-hand side. Sorry, the real part. Okay, so the real part here is actually coming from this summation here. Okay, so from this summation, we are going to obtain the right-hand side. Okay, so consider this summation is so this is like a sum to infinity of a GP. So A over 1 minus R. So the A here is Z, R is also a Z here. So we consider that one. Okay, Z over 1 minus Z. So we want to get the expression, okay, in the question there, right? So that is where, okay, we sub in the Z. So here you have to be careful. The Z here is not just the cos theta plus I sine theta that we always work with. Okay, it's a 1 over 3 of that. So when we sub in the Z, we have to be a bit careful. So it's 1 over 3. Okay, it's 1 over 3. So after that, okay, in order to sort of like tidy that up, we need to multiply by 3. So we clean up the fractions. So after we multiply by 3, right, okay, what we have is just this one and 3 minus the e power I theta. Okay, so that comes the part where we want to multiply by the conjugate of it. So if at the bottom there, well, after we multiply by 3, okay, we will get like 3 minus e power I theta. So here we have to multiply by the conjugate of it, which is 3 minus e power negative I theta there. So we have to do the same thing for the numerator as well. Okay, so it's a good thing that we do multiply. So we expand the top there, and then for the down here, when we actually try to expand it, it will give us some nice form, which is like this. So this e power I theta plus e power negative I theta is a 2 cos theta. So when we tidy up, this is what we get. Okay, so at last it's there already. So the bottom there, we do not have any complex anymore. So that is, we will compare the real part. So now because we want to actually obtain the real part here, right? So we expand everything here and we just compare the real part. So once we compare the real part, we can actually get the result that we want from there already. Okay, a slightly different questions here, right? Okay, so let's look at the matrix question. I don't think we have got other. Okay, let's look at the matrix question. So find matrix P and a diagonal matrix C such that the A squared is PDP inverse. So this is a usual eigenvalues, eigenvectors question. So first is that from A, okay, from the A here, we know that the eigenvalues are just all these. This is the upper triangular matrix, okay? So these are the eigenvalues of the A. Okay, so now we want to find the matrix P and the matrix D, right? But the matrix P and the matrix D here is the one for A squared. Okay, so we just need to recall, no matter it is A or A squared or any A power n there, the eigenvectors are the same. Okay, so for A and the A squared, they have got the same eigenvector. So we will find the eigenvector from the A first. Okay, so to find the eigenvectors from the A, we are considering using the A minus lambda I or lambda I minus A. Okay, so is to sub in each of the eigenvalue there. Okay, so you can see we sub in each of the eigenvalue there, and we cross the two rows, okay, which are not multiple on one another. We cross them. Okay, it's a bit of the value that we have to be careful to work with, okay, especially when they purposely put the 22/3 there. It adds up a little bit to the difficulty, okay, so you have to be careful. So if you have the calculator function to check, you may use that as well if you feel not so secure about it, okay, you can check also. So after that, okay, when we cross the three from the three eigenvalues there, we cross the rows, the two rows, we are getting eigenvectors. So these are the eigenvectors for the A, in which, okay, matrix D is the square of the original eigenvalue. So if A has this eigenvalue, A squared, the eigenvalue would be the squares of these numbers here. So I have to square the number here, as you can see, when we put them into the matrix D. So this is a matrix D. Matrix P is like what we said just now. Eigenvector stays the same, right? So we are just taking the eigenvectors that we have found earlier, and we just put them according to the order of how we put our eigenvalues there. Okay, so this is how we get these matrix P here, right? Okay. So, okay, in the part B here, so use the characteristic equation of the A here to find the A cube. So is to use the characteristic equation, yeah? So before this, we didn't do the characteristic equation. So it's lambda I minus A. We find the determinant of it and we equate that to 0 or the other way around. But we didn't really do that, okay? So we have to form from the eigenvalues that we have actually written down. So once we try to expand everything, so we get a QP equation here. Okay, so this QP equation here, we will have this Cayley-Hamilton theorem. So the characteristic equation will become an equation which is involving the matrix Okay, so from here, because we want to find the a cube, right? A cube is depending on this relationship here. So 31a minus a 30 identity. So here, we just have to sub in the a and the identity, then we carry out the working from there. Okay, so when they want to find the a cube here by using the characteristic equation, if we actually go and do like we multiply the a like this, we expand the a like this 3 times, it is not going to be accepted. Okay, because they already specified they want to use the characteristic equation to do it. Okay, so that would be the question 6. Okay, let's look at the question 7. So it's given that y is equal to shed of arc shed of x plus half. So express cos y in terms of x, and hence show that sin y divided x is given by this expression here. So basically, is to move the arc shed over first, and we inverse it so that we actually get a cos y. It's easier for us to differentiate that way. Okay, so we get the x plus half to the power of -1. So we just have to differentiate like with respect to x from both sides. So for right hand side, it's not difficult for us to differentiate. So it gives us the right hand side straight away already. For the left hand side, we get like a cos y. So differentiate cos gives us a sin. So a sin y, and we differentiated something related to the y, right? So we need to multiply the term by the dy dx. Okay, so this is why we get the first part A here. Okay, so the part B, find the first 3 terms in the Maclaurin series of the function just now. So what we have is that in here, we want to find the A, B, and C. So basically, the C is the coefficient of the x squared. If we need until the x squared term, we need the second derivative. Okay, so in order for us to get the second derivative, the easier way for us to achieve it is to differentiate from this relationship here. Okay, it is not to differentiate here from scratch again, yeah, is to use this relationship and we differentiate as usual to get the second derivative. So we don't necessarily need to have the d squared y dx squared as the subject there, as long as it is there in the equation. So we start differentiating the relationship just now. Right hand side, not difficult to differentiate. Left hand side, okay, is we have to use the product rule. Okay, so the product rule here is differentiate sin y, we get a cos y dy dx multiplied by the original dy dx there, so we get dy dx squared. Okay, it's not d squared y dx squared, yeah, it's dy dx times the dy dx there, so we get a dy dx squared. Then is to keep the sin y, differentiate the dy dx, so we get the d squared y dx squared. Okay, so later on, we have got all the expressions that we need already, so we sub in. So we sub in the x is equals to 0, then we are getting the y is actually an arc shed of a half. Okay, so for the arc shed of a half, right, there's one thing that we need to look at here is that if we have got the arc shed of a 1 over 2, it is equals to the arc cos of the 2. Okay, this result, yeah. Other related functions are the same, yeah. Okay, maybe I should use x lah, then you understand in this way. Okay, so it's to find the arc cos of the 2. So the arc cos of the 2, we need to use the formula, okay, of the inverse of the cos to actually find that. Okay, so after that, okay, what happened is that to facilitate our value evaluation later on, so once we have got the value of the cos y already, it's helpful for us to find the value of the sin y because we also need the value of the sin y later, provided that we know the cos y already. So we use the identity where the cos square y minus the sin square y is equals to 1. So we find out what is a sin y first, then later we can sum in very easily. Okay, so this is for the first derivative. So we have got sin y dy dx is equals to minus 1 over the 1 plus a half square. So here we can have the value of the sin y very easily already. Okay, so with that we can get the value of the dy dx. Okay, so don't go and, because you see this is like a sin y, right? So don't go and substitute this y value and evaluate it here, yeah, is going to be very painful, yeah, lots of work. So use this identity because we know cost already, supposedly we should know the shine as well, right? Okay, it's very painful, yeah, if you sub the lawn inside the shine to evaluate. Okay, don't do that. So use the identity here instead to evaluate. Okay, that's one thing that it could help us. So we have got the value of the dy dx already. Okay, so at last, we need to find out the value of the d squared by dx squared. So just sum in all sorts of the terms, like we have got the dy dx, we have got like a shine y, those kind of thing, and x equals to 0, everything. So we could get some nice value for the d squared by dx squared. So at last, just put them into the coefficients. Okay, so remember the coefficients, don't forget about all the factorial set. Okay, so after we evaluate those, so this is the value that we are getting. Okay, so the difficulty about this part of the question is the evaluation. So it's not really like a lot about the differentiation part there. The evaluation is the part that is taking us a lot of time. Okay, so you can see the numbers, all the constants like the coefficients are also like not so nice ones. Okay, so like the details like all the small stuff that allows us to work on the questions easier. Okay, is the one that we need to take note of. Okay, so okay, the last question here is also quite a bit of work. Okay, find dx dt and show that the dy dt is 1 minus sine square t. Dx dt, very easy to differentiate from here. And then the dy dt here, right? Okay, after we differentiate, okay, it's not difficult to do that also, but we are getting something which is in terms of like a cos 2t. So here it's only sine square. So we are going to use the identity, okay? Cos 2t is 1 plus 2 sine square t. Okay, so how to get this identity here, remember, is from the Osborne's rule. So whenever we have got, like when we want to change to the hyperbolic version, right? So cos 2x is 1 plus a 2 sine square x. Because this one has got the product of two signs. It's a sine square. So we need to change the negative to the positive in the hyperbolic version. So we apply that, tidy up, then only we are able to get this here. Okay. So the part B1, they want to find the surface area generated is given by this thing. Okay, it's a 4 marks question there. It's slightly, it is quite a bit of the things that we need to do. Okay, including, okay, so including in the formula, we know that it is 2 pi integrate y square root of the dx dt plus the dy dt squared, right? So let's say we simplify that one first, okay? The square root of the dx dt squared and the dy dt squared, basically we just expand everything. So the dy dt use the one that they actually gives us, yeah? It's easier, okay, to do our work later on. So, okay, expand everything, and this is what we get. Okay, and from here we need to cancel off with the square root there. Okay, so this is actually a perfect square that we can actually write it as a 1 plus sine squared square. That we can actually cancel the square root with the square there. So we only get a 1 plus sine square. But if you notice, there is no like 1 plus sine square there because obviously this is our y. Okay, this is our y. So there is actually no 1 plus sine square there. So the 1 plus sine square, you can see it is actually being changed to the form which is like the 2t. So instead of a t now, it has changed to the 2t. Okay, so 1 plus sine square, we know that it is actually a cos square. So here we are using the double angle formula again. So the cos 2x is 2 cos square x minus a 1. So we are making the cos x as the subject here. So with that, we are actually getting something which is in terms of the 2t. So after that, only we put everything inside there and multiply. Okay, then only we are able to get this form here. Okay. So of course, there is a purpose lah that they actually ask us to prove this because they need us to find the integral later. Okay. So it's quite a bit of thing to do here. Okay. You might have a slightly different way of working on it, but for myself, okay, I would just expand everything here because if you refer to the mark scheme, right? I remember the mark scheme actually just use these two terms to multiply with the whole thing, like the 1 plus the cos 2t, which might be an easier way for you to work on it. Okay, but for myself, I'm actually doing it like using like a little bit different method here. Okay, so okay, what am I trying to do in this case is that okay for the things which is like we have got this first part is very easy to evaluate. So I just do that first. Okay, I do it part by part. So the first part here, I have already done that very easily. Okay, it's some usual functions that we know how to integrate from there. And then we have to deal with like the rest of it. Third term, it's a t times a cos 2t. Okay, that is where we have to use the by part. So if you let the u to be 3 over 2t, so the dv dx, the dv dt here will be cos 2t. So differentiate the u, integrate the dv dt here, and put them into the formula for the by parts. And here we can evaluate them already. Okay, we evaluate them. This is what we get for the third one. And then the last one is to minus, okay, the 1 over 4 sine 2t cos 2t. For this one, okay, I'm actually looking at it as, okay, why do I get like a sine and a cos here? Because from there, I already like differentiated something that is like a sine square. Because differentiate a sine square is like, we bring down the 2, the sine becomes 1, and then we have to differentiate this sine itself. That's why I actually get a cos 2t there, something like that. Okay, so I'm using that recognition to do that. Or in other way that you could do it is that you could change to the sine 4t, okay, which is negative 1 over 8 sine 4t. Because because this is like a double angle formula, then you integrate accordingly from that. Okay, so once you integrate accordingly from that, you should get something which is like this. Okay, so let me tell you what is the good thing about doing in this form rather than having it in a sine 4t is because if you do this after you integrate, right, you are getting something like this, in which when you sub in the value, you will start with the cos form. Okay, I mean it doesn't matter that you start with the cos form there. Okay, let me just show you. Negative 1 over 32. It's okay because you can always use a double angle formula again. Okay, you can use the double angle formula again to express it in either cos form or the sine square form. Not an issue. Okay, but if I actually like try to do this, I integrate it in like directly such that I get the angle is 2t. So later on, I don't need to worry about that anymore. Okay, it's a lot of the integrations that we have to be super familiar with, okay, in this situation here. Okay, so when we are not able to like do the integration in one shot, right, try to break them down. So in my case, I actually break them down into separate parts that I'm able to handle them individually. Okay, so once everything is done, I will just put it back, okay, to the earlier things there. So everything, I just put it back, and later on, it is just about like simplifying. So you have got some expression which is in terms of like a cos 2, sine 2, and you might have some expression which is in terms of the sine square 2. So of course, this is not the definite expression because they could be related by the identities as well. Because the sine square can be written into something that is a cos square. So remember, cos square x minus a sine square x is equals to 1. So you might get other values from here as well, which is equivalent. Okay, so you have got different form that we might actually see in this case here.